let's actually estimate if we will get the right numbers, because we have the numbers over here. So this is also a good lesson for you to learn how to apply physics to real life. In real life physics, you will not get problems that say, hey, you have the radius is equals to whatever point, whatever times 10 to the whatever, and please calculate this. That's not how it works, right? In real life, you want to be able to solve problems by analyzing things and thinking, and estimation is a very important tool. So we're going to estimate the value of G. Okay. All right, so we have that formula over there. So what were we going to plug in? We're going to plug in, right? So we're going to find out, is this correct? So we'll plug in 6.67. Now, if I want to do this just in everyday life estimation, so you don't probably even want to pull out your calculator. You just want to get a rough estimate, right? So in this case, maybe you do want to pull out a calculator and see if the numbers match up. I encourage you to actually do that after I do this as well. But just as a general, skill from part of the course, right? So let's just round it to easy numbers, right? 7 times 10 to the minus 11. And you'll plug in the mass of the Earth, which, can you guess how I would round that? Well, of course, 6 times 10 to the 24th, and divide by the radius, right? So what am I going to round that to? Well, let's just round that to 6. That's fine for just a rough estimate. Maybe you want to do it 6.4 times whatever, but we'll work with easy numbers first, right? Times 10 to the what's that, right? So that's around 6400 kilos, right? So what does that mean? Because meters is notice I didn't put units for all of these because these are standard units. Then that's not a standard unit, right? That's not a base unit at least. So the base is meters. So I need to put a K. Well, what's a K? Well, K is 10 to the power 3, right? So it's basically times K. Anything times K is 10 to the power 3. So this is roughly 6.4 times 10 to the power of 3, and then 1, 2, 3, 3 more, so 6 and 4 times 10 to the power of 6 meters. Now I won't put the meters because the meters is the standard base unit. Okay, so I'm just going to work with 6 temporarily over here. To the power of 6 square. Don't forget the square. What does the square mean? The square means multiply this twice. Just write that. Okay, can you do this in your head? Yeah. Well, 6 cancels with 6. 7 cancels with 6. Roughly. Okay, if you don't, I'll show you what will that turn out, right? So you have 7 over 6 over here, and what's left? So you have minus 11 plus 24 divide, so these becomes negative on the power. 6 and 6, right? So you need to minus, so this is really 10 to the 12, so minus 12, like this, okay? So 7 over 6 is going to be roughly 1. That's fine. So that's going to be 1. So we're not going to write that. What do we have here? We have 11 plus, well, this part's easier to do. 24 minus 12 is 12, right? Positive 12. So minus 11 plus positive 12, that's 1. Is that what you expect? Yeah, well, let's put in the units at the end, right? Meters per second square. We know that as the acceleration. That's an acceleration due to gravity. And that's exactly what we want. All right. So as you can see, you can plug in the correct numbers. Of course, this is not how historically it came about. Historically, it's sort of flipped around. This is something you can actually measure on Earth. And what you can use this to do is find out what is the mass of the Earth. So this is something you can actually measure, right? Just drop a couple of objects and you can measure how much they accelerate using your SUVAT equations, right? You calculate the time, you measure the time, you can back your way up and find out what that value is, or just measure how much it accelerates. It's very easy. The radius, so out of these couple of symbols, which one, so this is measurable. The radius is also measurable. This is actually done all the way back in the Greeks. Not very accurately, but still doable, right? So still some people argue that the Earth is flat, but even the Greeks know that that is not true, because you can have a pole, put a pole over here, right? When the sun is on top, right? So there's no shadow. if you walk a little bit further to here, you put a pole, right? And then when at the exact same time of the day, suddenly you'll realize the sun is casting a shadow. And that depends on the curvature of the Earth. Now you can easily, just by a couple of trigonometry, we're not going to go through the whole trigonometry problem, but it's a simple trigonometry problem. So you can figure out what's the curvature, you can calculate the radius and the circumference of the Earth, right? So the radius is something you can easily figure out, even without calculators, with elementary techniques. So once you measure this, you know this is a universal number, right? You can figure out the mass of the Earth. Or if you don't know the G, like Newton does not know what that is, right? You need to figure out that. So if you can find an alternative way to measure the mass, you can figure out what G is, okay? So you can look up Cavendish, and one of Newton's, the scientist in Newton's, Cavendish, hope I spelled it right. You can double check that on Google. Another British physicist, it was the first guy who determined the mass of the Earth. So people credit him with the first person who weighed the Earth. And you can look up the Wikipedia of his very brilliant scientist who have done great things, not very talked a lot about in a lot of courses. So well, you can look that up if you're interested. Now that you understand how this works, I have a question for you. So we understand really there is the formula over here is plus h before you square, right? You need to add the height of this. So can you find out what is the value of G when you go on top of a really tall mountain? Let's say Mount Everest, right? So now you have the Earth, right? And then there is Mount Everest. So what is the value of G over here? So I'll tell you the height of Everest, for example, is 8,900 meters, I think, if I can find it somewhere. Yeah, sorry, 8850 meters. Okay, so what is the value of G on Everest? Okay, compared to the G on sea level. So we'll assume this is our Earth, and that's our that's the height of Mount Everest. So go on and run the numbers, and I think I got the value of G on Everest is 9.77 meters per second square. As you can see, there's a tiny difference between 9.81 meters per second square. Okay, so see if you get the same value, and now you understand that G is not really a constant. It really depends on a couple of things, in particular, how high you are from the center of Earth.